Hello there. In this video, I want to build off of what I spoke about in the last video with regards to simplifying radicals, and I want to talk about rationalizing a denominator today. But before we talk about rationalizing the denominator, I want to talk about division. What does it mean to divide? So say we've got the fraction 4 over 2. This is 4 divided by 2. And in layman's terms, this means we are taking 4 and dividing, say we have 4 objects, okay? We're dividing them into 2 groups, okay? And then, so how much is in each group? Well, this would be 2, and so this would be 2 groups of 2. This is the basic idea of what division is. Let's talk about another one. Let's talk about 7 divided by 2. Well, this we know to be 3 1/2, or 3 1/2 written as a mixed number. This would be 3 groups of 2 plus 1 remaining. So that might be a 4th group, make sure I can spell correctly, remaining. So that might be a 4th group with just 1 in it. Again, this is the idea of division. Let's talk about one more. 1 divided by 2. This would be 0.5. So this would be 0 groups of 2 with 1 remaining. So now the purpose of the video, let's talk about 1 over the square root of 2. Square root of 2 is an irrational number, so we can't write it as a fraction of integers. So we can't use anything like reciprocals to take a complex fraction and simplify it. We have to do something else. This effectively means, in our traditional rules, take one object and divide it into groups of square root of 2. What does that mean? How can you take something and divide it into square root of 2? This is where I think there was a misapprehension in my education as a student. When I learned about rationalizing denominators, I always interpreted it to be like dividing by 0. We can't take, say, 3 and divide it by 0. If you type that into your calculator, it's going to yell at you, okay? I thought if I typed in 1 divided by square root of 2, it's not going to be able to compute it. I have to rationalize the denominator. I'm not blaming my teachers for mischaracterizing this. It was a long time ago. I can't remember exactly what I was taught. I just always assumed you can't type this into the calculator. It turns out they teach us to rationalize denominators because of this idea of taking an object and dividing it into groups of square root of 2. That doesn't make sense, and it doesn't really fit with the traditional idea of what division is. So when you get into higher forms of advanced math, this is a skill that generally tends to fall by the wayside because college professors may not necessarily care if you rationalize the denominator. However, when you get into calculus and some of the more long-formed algebraic type problems, knowing how to rationalize a denominator is a very handy skill. So what I should say is, in higher forms of math, it's handy when it's algebraic, but when it's computational, it's not entirely looked upon as necessary. So what do we do? Well, when I think about what that means, rationalize the denominator, it means I want the denominator to be a rational number. So I want to add or subtract or multiply or divide by something that is going to give me a rational number in the denominator. Well, I happen to know this. If I take square root of 2 and multiply it by square root of 2, this becomes the square root of 2 times 2 using properties of radicals. These are both positive integers, so I can combine them into one radical, which becomes square root of 4, which becomes 2. The long way of just doing the calculations out. The shortest way is to say square root of something times itself. Is it squared? The square and the square root cancel out. Now, like everything we do with fractions, if I do it to the bottom, I also have to do it to the top. Now, this is a nice example to start with because 1 times anything is square root is itself. So this, in case, would be square root of 2. So my final answer is square root of 2 divided by 2. Now we can reinterpret this to look like how we usually want division to look like. I take square root of 2 objects and divide it into groups of 2. That makes a little bit more sense. Yeah, you can't have square root of 2 objects, so maybe we look at something like a length of square root of 2, and I divide it into 2 as opposed to taking a length of 1 and dividing it into square root of 2 partitions. But this makes more sense with what we've come to know division. Let's look at another example. Let's look at 1 over, say, the cube root of 3. Well, now we've got a cube root. So if I go ahead and I multiply by a cube root of 3, that's not going to be enough. I need to be able to do it 3 times. So I'll have to multiply it by cube root of 3 or cube root of 3 squared, which is 9. Obviously, the way I laid this out, I'm multiplying by cube root of 3 times cube root of 3. But if you had jumped to cube root of 9, that is also an acceptable answer. In fact, that's what I'll put up top. I'll put cube root of 9. And so, cube root of 3 times cube root of 3 times cube root of 3. Well, all the cube roots just cancel out, and I just am left with 3 in the denominator. And 1 times anything, again, is itself. So I get cube root of 9 up top. All right, I want to do one more example, and this one's a little bit more complicated, but I find it fascinating, and it kind of lays the groundwork for things that I'm going to do in the future. So if you want to stick around for this problem, otherwise, I've taught you the basics of what it means to rationalize the denominator. In this problem, I'm going to do the cube root of 2 plus the cube root of 5 in the denominator. Now this becomes a little weird. There's a formula I can use, and here's what I have to multiply. So I have to treat this as an entire quantity. I'm going to multiply it by, I want this cube root of 2 to eventually be 2. So why not multiply by cube root of 2 squared? Okay, great. I also want this cube root of 5 to be a 5. So I'm going to give myself some space, and I'll cube root of 5 squared. Now, if we distribute this as is, it's not going to completely pan out because of the way distribution works. We're going to have some terms left over. So I'm also going to subtract and multiply by the cube root of 2 times the cube root of 5. And that'll be my quantity. You probably recognize this as the difference of cubes formula, or in this case, the sum of cubes formula. If you don't recognize it, that will be a video coming in the future. So for now, you'll just have to take my word for it. Whatever we do to the top, we do to the bottom. So cube root of 2 squared minus cube root of 2 times cube root of 5 plus the cube root of 5 squared. All right, so I can just simplify the numerator, cube root of 4 minus cube root of 10 plus the cube root of 25. Really quickly, if I multiply the cube root of 2 times the cube root of 4, I get cube root of 8, which is 2. But then I have to go ahead and I have to multiply that by each. So I get cube root of 2 times cube root of 2 is cube root of 4 times an additional cube root of 5. That's cube root of 20. And then I get cube root of 2 times cube root of 5 squared. That's cube root of 50. And now I have to repeat that process with the cube root of 5. So cube root of 5 times cube root of 2 squared, that's a cube root of 20. So plus cube root of 20. And then 5 is 25. times 2 is 50, and I got the minus, so minus cube root of 50. And then I get cube root of 5 times cube root of 5 squared is cube root of 5 cubed. So that gives me my plus 5 at the end. Now this is where that extra term came in. Notice this and this cancel because they're just opposites. This and this cancel because they're opposites. And I get 2 plus 5 is 7. And then I'll rewrite the top. And now this is a good time to mention, can I simplify the numerator? No, I can't. And I will go over why in the next video. But for now, this is my final answer. Be sure to give this video a like and subscribe and leave a comment down below. And I will see you for the next video. Thanks for watching.